Now that you know what the fundamental operations of set theory are, union, intersection, and complement, we want to talk about how to do analysis with those operations. These operations are very similar to the logical operations and, or, and not. So if you follow this link here, you can see how these operations act very analogously to those. The first thing we want to discuss is order of operation. And the first operation that's always performed is complement. Then, at the next level is intersection and union, which are on the same level. Parentheses can be used to change the order of operations or to impose an order of operations. So for example, if I want to do a union first and then a complement, I put parentheses around the union. So let's look at an example. We're going to take the universal set U to be 1, 2, 3, 4, 5. And we're going to have two sets. A is 1, 3, 5, and B is 1, 2, 3. So if I want to compute A union B complement, that would be 1, 3, 5, which is A, union 1, 2, 3 complement, so which is B complement. By the order of operations, the complement is performed first. So we're going to take 1, 2, 3 complement and compute that, which gives us 4, 5. Then we compute the union. So the union of 1, 3, 5 and 4, 5 is 1, 3, 4, 5, all the elements in both sets combined. However, if I wanted to compute the union first and then the complement, then I would need to use parentheses to impose the order of operations. So A union B with the parentheses, and then the complement on the outside. To compute this, we would take A, 1, 3, 5, union B, which is 1, 2, 3, and get 1, 2, 3, 5. The complement is just floating on the outside. Then we would take the complement of 1, 2, 3, 5, which is 4. So notice that the order of operations matter. If I take the complement of B first and then the union, I get 1, 3, 4, 5. But if I take the union first and then the complement, I have the set that only contains the element 4. Now let's look at some of the basic properties of these operations. The complement is the only unary operator, which means it takes one input, and it gives us an output. And the most fundamental property of complement is that if you take the complement twice, you get the set that you started with back. So for any set A complement equals A. We can prove this claim. So if X is an element and A complement, then X is an A, and if X is an A, then X is an A complement. That would mean that A complement equals A. So whenever we're doing a proof of sets like this, this is typically what we usually show, is that if X is an element in one set, then it's in the other, and if it's in the other set, then it's in the first one. But we could also derive this logically. So X is an A complement means, well, this outside complement means the negation of X is an A complement, or in other words, X is not an A complement. And to say that, and here X is an A complement means to say that not X is an A. Then we cancel the two negations. So double negation gives us just X is an A. And therefore this statement, X is an A complement, is equal to the statement X is an A. Or in other words, it's logically saying the same thing. The operations intersection and union, the important facts to know about those are they are commutative and associative. In other words, it doesn't matter what order we do them in as long as the operations are all the same. That would be associativity. So to state that for intersection, if we have three sets A, B, and C, if we do A intersect B first and then intersect C, that's the same as doing B intersect C first and then intersect A. And for that reason, we usually don't even use parentheses. So down here, we state that we can even write A intersect B intersect C, and that's well defined because of the associativity of intersection. And that works for union as well. Commutativity means that the order of the sets don't matter. So A intersect B is the same as B intersect A. Doesn't matter which one comes first. Same thing with union. So A union B is equal to B union A. And now that we've seen some basic properties of each of the operations, we need to know how the operations interact with one another. So the union distributes over the intersection, and the intersection distributes over the union. In other words, if we have sets A, B, and C, then A union, the set B intersects C, so with A union on the outside, this will distribute to the inside. A union B intersects A union C. So we take this A union and put it inside both parentheses. And then the intersection comes onto the outside. Similar with A intersect B union C. So this A intersect goes inside this first parenthesis and the second parenthesis. So it's the A intersect gets distributed to both parts, and then the union is on the outside. We can derive these logically. Once again, it follows from the distributivity of and or over one another. So to say that X is in A union B intersects C is to say that X is in A or X is in B intersects C, because remember that union means it's one or the other or both. So it's a logical or. Then to say that X is in B intersects C means that X is in B and X is in C, because for something to be in the intersection of two sets means it must be in both sets. And then here, the or distributes over the and. So to say that X is in A or X is in B and X is in C is to say that X is in A or X is in B and X is in A or X is in C. Then we just reverse the steps back into statements of set theory. So to say X is in A or X is in B is to say X is in A union B. And to say X is in A or X is in C is to say X is in A union C. Then we have X is in A union B and X is in A union C, and this and becomes an intersection. So X is in A union B intersect X is A union C. So switching back and forth between logic and sets, we can derive a lot of these sort of fundamental rules of how these operations interact with one another. And a similar thing happens for what is called De Morgan's laws. So this is how negation or complement interact with, well, if we were to talk about negation in logic and an or, and for set theory, complements interact with intersection and union. So if we have A intersect B complement, the whole quantity of this complement, we can distribute the complement to A and B, but this operation flips over. So instead of intersect, it becomes union. And similarly, if we distribute a complement over the union, it becomes an intersection. So that's the thing you really got to remember, is when you distribute a complement by De Morgan's law, you have to flip over the inside. And we can verify this statement. We're going to do one of them. So we're going to show that A union B complement is equal to A complement intersect B complement by showing, again, that the two statements are logically equivalent. So X is in A union B complement means it's not the case that X is in A union B. So we get a negation out front of a statement that X is in A union B. Then the statement X is in A union B just means the statement X is in A or X is in B. It's got to be at least in one or the other, or possibly both. Then, if you go to the lesson on logic that I pointed to, you're going to see De Morgan's law for negation and disjunction or. So we have not, it's like P or Q, and if we distribute the negation, this symbol gets flipped over. So the or becomes an and this is not X is in A and not X is in B. Then we revert this back to statements of set theory. So this not becomes a complement. To say X is not in A is to say X is in A complement. So that's this and this. And then to say X is not in B is to say X is in B complement. Then we have X is in A complement and X is in B complement, meaning X is in the intersection of A complement and B complement.